So today we are going to learn about electrolytes, okay? And even though we haven't learned about it yet, I know that we have heard of the term. Okay, so electrolytes, athletics, right? Football players get these like little white tablets. They're electrolyte tablets. One of the very few athletes who actually need to replenish their electrolytes, because football is a summer basically it's a summer sport in Texas, right? And it's hot and they sweat a lot, and when you sweat you lose electrolytes from your body. To replenish those, this is sometimes not enough. You just literally have to straight up take a tablet, right? How can you tell if your body needs an electrolyte? If you're sweating a lot, especially if you see these like white streaks on the back or even on the front sometimes for people who sweat a lot, right? What are those? Those are salts from your body that are basically oozing out with sweat, right? You need to replenish those. If you're drinking one of these as a drink with your lunch, probably, not the best idea. At the best, you're wasting all the electrolytes. So whatever you're drinking, all of those are just coming out in your pee, right? Worst case, you're overloading your kidneys, because your kidneys have to do extra work to get rid of all these extra electrolytes that you put in there. So, that's my little 2-minute rant. Now, electrolytes are important in our body, but we also have to understand that the word electrolyte actually has nothing to do with like the physiology of your body, but with this. What do you think I'm talking about here? What did you say? Electricity. That's where the word electrolyte comes from. Okay? So, we will define the word electrolyte by saying a substance that conducts electricity. Okay? I wouldn't even call this an apparatus, because it's literally just a lamp that I snuck out of the house that my wife doesn't know yet. What I've done is, this just plugs straight into the outlet. Couple of things that I want to make sure that all of you understand you should never, ever do. Okay? And the first thing, you should never daisy chain. This is what it's called, daisy chaining. An outlet, like a power strip into another power strip. Never ever do that. The only reason why I have to do it is because I don't have an extension cord, and all I'm putting on there is just one little 20-watt LED bulb. Okay, so it does not draw a lot of current. So just for the purpose of this experiment, I have my fire blanket and my fire extinguisher over there. Electricity is not to be messed around with, okay? I have literally spent months and months learning about all these things, okay? And so that's why I feel somewhat comfortable doing what I'm doing. You should absolutely never do this, okay? So we all know what happens, right? Like when you plug in a lamp and then you turn it on, which I've left this on because I want to show you something, that how does electricity flow, right? So we'll go ahead and plug this in and it's on. So right now, why does the lamp turning on?
Because you got no current.
Because there's no current, right? What is electricity? Electricity is just electrons coming out from that outlet through this black wire into this wire. And where are all my electrons right now?
At the end of the day.
Right here, at the tip of this wire, right? If I were to accidentally touch that bare metal, I would have a very bad day, right? Because those electrons are just dying to go somewhere, but they don't have a path, right? Because I have disconnected or broken the circuit, right? Now, here's the other half of the wire, right? Here's the other part of the wire. And if I do this, it turns on, right? Because now the electrons that were on the tip of this wire have somewhere to go. So where do they go? They go into this wire, that's my right hand. And from here, they go into this lamp. They light up the lamp. And then whatever leftover electrons, well, I shouldn't say leftover electrons, all the electrons, after doing the work, which is turning this light bulb on, right, are going through the other wire that I did not cut, right? Flow back into this surge protector, back into that surge protector, you should never do, and it goes back into the grid, right? Electricity is nothing but high energy electrons coming from one wire, flowing through your appliance, doing whatever you want it to do, and then going back into the grid, right? The entire electrical grid is a closed loop, okay? Electrons just flow, filled with energy, do whatever they need to do, and go back, okay? Now, these are made from copper, and we all know that copper is a good conductor of electricity, right? Nowadays they use aluminum because A, aluminum is a lot cheaper, and B, it's a little more malleable and ductile, so it's easy to extrude aluminum wires, but they don't carry as good of a current, okay? So if you look at like how thick this is, right? This is made from copper. But if you look at the wires that come in like your little lamps, fixtures and stuff like that, nowadays they're all aluminum because they only need to carry a little bit of current, so it's cheaper. Anyway, so electrolyte, however, is not the same as bare metal, okay? An electrolyte is a substance other than metals that is also able to conduct electricity. So, in front of you, I have a whole bunch of chemicals, right? I have tap water, distilled water, Gatorade. Right now, this is only distilled water. I'm going to put something in it. This is ethanol, which is just, you know, alcohol that we make beverages out of, and then vinegar.
Ew.
So we are going to test all of these, and using these 6 examples, we are going to learn what is an electrolyte, what are the different types of electrolytes, and is everything an electrolyte? Okay, so let's start with our first candidate over here, which is tap water. Now, before I do this, what is our prediction? It's unplugged, right?
It's unplugged.
Okay, so when I do this, do you think it's going to conduct electricity?
Yes. No.
How many yeses?
I don't know.
Okay, typically, anytime you buy like an appliance, especially the one that's going to be around water at your home, right? Like your flat irons and your hair dryers and any outlet that you have in your kitchen, for example, has a little breaker switch on it, right? It like goes back and forth anytime, and it says you tripped a GFCI outlet, right? So that's because water that comes out of your tap is not the same as regular water. So let's see. Let's go ahead and plug that in. Okay, it's on. Nothing's happening because the electrons are still at the tip of this thing, right? And then they go in and it lights up.
Yo.
They're not touching each other, right? See? They're on the opposite ends of the beaker. They're not touching each other. And so what's happening is electrons from the tip of this wire jump into the water. Go ahead and turn that on. They're jumping into this water. Right now, do they have anywhere to go though?
No.
So where are they?
In the water.
They're in the water, just waiting to go somewhere. As soon as I put this wire in, circuit is completed. Right?
I mean, it's not as bright, but I mean.
Not as bright. Good observation, because here's how much bright it's really supposed to be. Yes?
Yeah.
This is how much bright it is. Not the same. So, it's unplugged. I'm going to wipe these off, make sure they're nice and dry, so we do not contaminate the samples from one to the next. Okay? The second one is distilled water. So let's try that. Okay, electrons are on the left hand, no electrons on the right. Dip this, nothing happens, and nothing happens. This is distilled water.
What's that?
What is distilled water?
Purified water. Like
What?
Like the water that we drink?
So purified water is just water that has been really filtered well. It's called purified water. Not to be confused with distilled water. Distilled water is when you take, hopefully purified water, and you boil it.
Oh,
And when you boil water, it turns into
hot water.
gas, steam, right? And then you collect all that steam into a separate container. And you condense the steam back into water. And what you're trying to do, what you're hoping to do, is everything that makes this tap water conduct electricity is left behind, and you get distilled water. And so really, the all-important question is, what is in my tap water? What is present in my tap water that is absent in my distilled water? Something in here causes electricity to flow. Something in here prevents electricity from flowing. So what do we think?
Type of like metal. I don't think that was right. Never mind.
It's okay. No, but
Like some type of metal in the tap water.
that is like 98% right.
Salt?
Okay? What we have dissolved in water are electrolytes. Okay? It are these electrolytes that are conducting electricity. And so, let's go ahead and define electrolytes. We will define electrolytes as all ionic compounds. All ionic compounds that conduct electricity when dissolved in water. Okay? We tested when it's by water itself. Did you conduct any electricity?
No.
No. But when there was stuff dissolved in it, like metal ions and other anions, they are the ones who were conducting electricity. Okay? So, electrolytes, the word electrolytes come from electricity, and we just saw what happens, right? Electrons need somewhere to go because they like to flow, but they have nowhere to go. So think of electrolytes as little shuttles, like when you go to the airport, right? There's a shuttle that takes you from like your car parking lot to your terminal, just back and forth and back and forth. That's what tap water has, electrolytes. Little ions that act as shuttles that take your energy-rich electrons from the, what we call a live or a hot wire, because it's coming straight from the outlet, to the path of least resistance, basically, right? So they exit through this wire, go into the solution, travel with the ions, because those are their shuttles, go in here, light up the lamp. Okay? Now, we noticed how this was not very bright, right? Let's go ahead and verify that one more time. Okay, so now this is a live hot wire, fairly bright, not as bright, right? What inference can you make from this? Why is it not lighting up a lot?
It loses some of the electrolytes in the tap water.
Think about how we compared these to like shuttles at the airport, right? There's a lot of people here, right? People being electrons, right? A lot of people just waiting to get on the shuttle. Very few people will make it to the other side though. What does that tell you? There's a few shuttles, right? There's very few electrolytes in here. That's why that lamp is dim. That makes sense? Right now, there's a lot of shuttles. Shuttles being electrons. I mean, conductors, right? So, this is bright. Try our favorite, Gatorade, and see what happens. So let's go and plug that in.
The same as the first one.
I would say so, right? It's about the same brightness as when I connect them together, right? What does that tell you about Gatorade then?
Has more electrolytes.
It has a lot more electrolytes compared to that of water. Next, what we're gonna do is see if we can modify this distilled water, right? So it says distilled water plus something, but I haven't added anything to it, right? And we're going to verify that by trying to complete the circuit, and it doesn't light, right? So we know for a fact that there's nothing mixed in here that will conduct electricity, right? Now, until last class, well, let's do this. I am going to crush up a little bit of chalk. Chalk is basically just an ionic compound, calcium carbonate. So what I'm gonna do is break into little pieces. In the video, this is where I put that, that 2 hours later. And then I add all of this to it. Now, we learned last week, using the list that's on the back of the periodic table, that carbonates are insoluble compounds, right? So if you come across a chemical whose name ends with the word carbonate, most likely it is going to be an insoluble compound, right? The only exceptions are ammonium and the first group elements, which are your alkali metal ions, right? So something like sodium or potassium carbonate does dissolve in water. Ammonium carbonate does dissolve in water. Any other carbonate, on the other hand, stays insoluble. So that's what I'm going to do. I'm going to add this calcium carbonate to water. I'm going to give it a good swirl, but you will notice how all of that is still just undissolved and like it's made the water milky, right? We know it didn't dissolve. So now let's try that. Okay, so it works. This goes in here. Let us contrast. I'm going to get some distilled water. We are going to verify that it does not conduct electricity. It doesn't. Okay. It doesn't. Okay. Now, I'm going to take a little bit of salt, just a little shake. That's it, like you can barely see any. There's like 2 crystals on the bottom. So, give it a nice stir, make sure all the salt dissolves.
Crazy.
Okay? So it was literally just like a tiny little shake, like not even like a whole gram of sodium chloride, and you saw how much electricity was being conducted, right? And so electrolytes can now be classified into 2 categories: strong and weak electrolytes. Okay? An electrolyte can be categorized as a strong electrolyte and a weak electrolyte. All ionic compounds are some kind of an electrolyte. What is the difference between sodium chloride and calcium carbonate.
Contains metal.
Well, to be fair, they both contain sodium, which is a metal, calcium, which is also a metal. But what did we say about their solubilities?
Oh, they, you can different amounts, right?
This is completely soluble, right? This, on the other hand, we said it was insoluble, but really, the correct chemistry term is slightly soluble. Okay? What I want you to realize is that all ionic compounds are soluble in water. Okay? I know that the back of your periodic table says soluble and insoluble, but that's not really the case. Okay? It is soluble compounds and then slightly soluble compounds. Sodium chloride falls under the soluble compounds category. Calcium carbonate falls under the slightly soluble compound category. Okay? We just demonstrated that. The only way calcium carbonate can conduct electricity is if it dissociated. Remember that word we learned last week? What does it mean to dissociate?
Separate.
To separate. Which means that the calcium in the calcium carbonate is, okay, this calcium in calcium carbonate is being pulled apart from the carbonate, right? Now, the difference between this and this is that if you have 100 molecules of sodium chloride, right? Let's assume that you have 100 molecules of each. 100 of sodium chloride, 100 of calcium carbonate. Every single one of sodium chloride is going to dissociate. All 100 of them. Okay? After I gave it a stir, I don't have a single molecule of sodium chloride hanging out in the water by itself. Every single molecule of sodium chloride has dissociated. Okay? And until a compound, an ionic compound, dissociates, it cannot conduct electricity. Okay? Only dissociated ionic compounds conduct electricity. Okay? Sodium chloride dissociates a lot, all of it, right? So it conducts a lot of electricity. That even a tiny amount makes more ions than the entire chalk made, right? So, sodium chloride is a strong electrolyte. Okay? So for strong, we will write they dissociate completely. Strong electrolytes are ionic compounds that dissociate completely. And then by extension, weak electrolytes must be,
Associated.
well, we will say they dissociate sparingly, right? These are some of the terms, like you will never see or hear the word sparingly. At least I haven't in my 37 years of life, except for a sparingly soluble salt. That's it. Electrolytes dissociate sparingly, right? Means very slightly. So if you were to take 100 molecules of calcium carbonate, like maybe 3 or 4 will dissociate. Compared to 100 molecules of sodium chloride, every single one of them will dissociate. Okay? So that is the difference between a strong versus a weak electrolyte. Okay? Which then leaves only one question to be answered. What do we do with compounds that do not conduct any electricity? What do we call them? They're then called non-electrolytes. So, what are non-electrolytes then? Non-electrolytes are all covalent compounds. All covalent compounds fall under the category of non-electrolytes, including our good old water. And we have proven that. Yes?
Yes, sir.
We demonstrated how water in its pure form does not conduct electricity because it needs the ions to do the conduction. Water has no ions, so it does not conduct any electricity, right? But when you add stuff to water, when you add ionic compounds to water, it gives them the shuttles that conduct the electricity. Okay? Now, I have a couple of more chemicals just to like drive the point home. So, go ahead and turn that on, right? We'll verify this is still working. The next in my list is alcohol, ethyl alcohol, okay? And notice that it's not lighting up. Because ethyl alcohol then must be what kind of compound?
A non-electrolyte.
A non-electrolyte. And the easiest way to tell if something is an electrolyte or not is if it has a metal in it. Okay? But because you already know that I can't just like, let everything be plain and simple and easy and straightforward, right? I'm going to now take a chemical that doesn't have any metal in it. Right? This is vinegar, a very common compound, right? All of us have it in our pantries. Vinegar has this chemical formula. CH3COOH. Is there any metal in here? No, which is why it falls under a. However, something that makes it ionic instead is this right here. So what ends up happening is that the CH3COO part separates from this H. And what you end up with is an H positive and a CH3COO negative ion. And if you look in the back of the periodic table where that list of polyatomic ion is, you will see the word acetate.
Oh, yeah.
This is called the acetate ion. However, this is a weak electrolyte.
Yeah, it's not important.
Right? It's not as bright. It is not as bright as this, right? Noticeably dim.
It's brighter than the water.
It is brighter than the tap water, right? So that these are some of the examples of electrolytes, non-electrolytes, strong electrolytes, weak electrolytes, right? How can you demonstrate if something is a strong or a weak or a non-electrolyte? By being able to measure the amount of current that it can flow through, right? But that's just how you can tell. Why does it happen? It happens because of dissociation, okay? Dissociation is the key. The brighter this light is, tells you a lot of dissociation must have happened. If this light is dim, it should tell you that hardly any dissociation happened, right? The brightness of this light is directly proportional to the number of ions present, right? The number of ions, on the other hand, are directly proportional to dissociation. More dissociation, more ions. More ions, more electricity, and a brighter lamp. Okay? So this is everything about electrolytes. On Canvas, you have a small assignment. I think I have like 4 or 5 questions that you need to answer. The last one is the one that's descriptive. The first 4 are just like a single sentence answer. Okay? So go ahead and get those answered.